Hello, and welcome to the beginning of week 4 of statistics at Washington State College. We are going to talk about probability. We'll get started on that this week. Maybe we'll get started if my computer will listen to me. There we go. We've got some basic objectives, and we'll talk about the vocabulary in these in a minute. Really, well, let's move right into the vocabulary. So with probability, there's some concepts some vocabulary we use to describe things. Um, a probability experiment or a trial is any process where the result is completely random. So flipping a coin, rolling dice, something like that, that the result is determined by chance. What hand you get in poker, whatever. Um, uh, chance of winning the lottery, all of those. So each possible result is an outcome, right? So if I'm rolling a standard six-sided dice, I can get a 1, 2, 3, 4, 5, or 6. Each of those is a separate outcome. If I've got a pair of dice, each potential combination is a separate outcome. Sample space is all of the possible outcomes. So 1 through 6 is each part of the sample space. Um, an event is a subset of outcomes. So like rolling an odd number on a dice, 1, 3, or 5. That would be a subset. That would be the event. Um, rolling, if I'm rolling a pair of dice, anything that adds up to a 7 would be, that would be a subset of the possible outcomes. So that would also be an event. So as I said, examples are drawing a raffle ticket, tossing dice, flipping a coin. Each of these has more than one possible result, and it's randomly determined. Okay, so let's think about a coin being tossed and a six-sided die being rolled. Die is singular for dice, which is plural. I tend to trip over that. I imagine most of us do. It's not very common to talk about die singular. All right, so what are the outcomes in the sample space for this experiment? Remember, we've got two things. We've got a coin being tossed and then a die being rolled. So one experiment includes a coin toss and a die roll. So take a minute. Think about all the possible outcomes. So when you're ready to move on, unpause. Let's next, if our event is tossing tails and then rolling an odd number, what are the possible outcomes that fit in that event? Okay. So we've got a head toss and a die roll. Probably we're going to want to come up with some sort of notation to make this easy to keep track of. So we could denote the coin toss as head and H or a T for heads or tails, and then the number on the die. So our sample space can be written fairly easily using that as, heads and a 1, tails and a 1, heads 2, tails 2. So, laser pointer. Got the laser pointer. There we go. There we go. See, heads into 1, tails into 1, heads into 2, tails into 2, etc. on down the way. So which one of these events fit tossing a tail and then rolling an odd number? Look about this. Tossing a tail gives us this column. That notation and that layout makes it easy to see. So we get T1, T3, and T5, the three outcomes that fit into that event. All right, so let's imagine we had two different colored six-sided die. So would be easiest if we wanted to list all of these, it's going to be easiest to come up with some sort of pattern to list the outcomes. So take a minute, come up with a pattern that you think will help list the outcomes, and go ahead and do that. And try to list all the outcomes. And then once you've done that, list the outcomes in the event where the sum of the numbers rolled on 2 die equals 6. All right, the book chose to start with keep holding the red die at 1 and varying the blue die, then holding the red die at 2 and varying the blue die. So that's going to give you, for example, this. Red 1, blue 1, red 1, blue 2, red 1, blue 3, red 1, blue 4, and on. Then, it's going to be red 2, blue 1, red 2, blue 2, red 2, blue 3, etc. So you've got this whole pattern here. You could look at it this way, where the red one is constant in each row, or you could look at it this way, where the blue one is constant in each column. Either way, they went ahead and added the sum here because we know we're going to need that for the next part. And that makes it easy to pick out everything that's going to give us a 6. Right, that's that diagonal right there. One thing to note, and they'll cover this in the next slide, that this result for 3, 1 on red, 2 on blue, is a separate outcome from this result that gives a 3, 2 on red, 1 on blue. The sum is equivalent, but the position of the die of the two dice are not. So it is a different outcome. If the die were identical, we wouldn't be able to tell. So again, they've just gone through and grabbed all the values that were on that diagonal. Pair of threes, the 4 and 2 combinations, etc. That is one way to list possible outcomes of something. Come up with a pattern and make a nice big table that shows everything. You can also do what they call a tree diagram. And it's useful when you've got multiple stages where the next stage is based on the results of the stage above it. Then when you get to the bottom, the number of possibilities in the bottom row is the number of outcomes in your sample space. So let's think about a family with 3 children. And I'm not going to encourage you to pause here because you've not seen a tree diagram unless you're looking at the textbook as well. So this will be your, an example giving the introduction to the tree diagram. So we've got, we want to find the sample space for the gender of each child in regard to birth order, which is actually very grammatically unclear question, and I'm not entirely sure, based solely on that, what they're trying to ask. So let's see what they've gone with. Okay, I see. So we've got 3 children. Each child could either be a girl or a boy. We don't know what order they were born in. Branches for each other. Okay. All right, so we've got the first child could either be a girl or a boy. If the first child was a girl, the second child could either be a girl or a boy. I don't know what the Okay, so the family shown in red is there to highlight what the notation is. The shape, um, triangle for girl, square for boy, denotes the gender. So the first child, it could be a girl or a boy. If the first child's a girl, then the second child could be either a girl or a boy. Um, Same with if the first child was a boy, it could be a girl or a boy. Then the third child, if the second child's a girl, the third child could be a girl or a boy. So we could have a pattern where the children are girl, girl, girl. We could have a pattern where they're girl, girl, boy, GGB, or the one shown in red, girl, boy, girl, um, and on down to boy, boy, boy. Um, so that would be one way to show the sample space, as well as kind of graphically figure out the notation to make sure you don't miss anything. You could think about this in terms of a pattern. You hold the first one constant, hold the second one constant, vary the third one. So you've got girl, 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 boy. Then hold the first one constant, take the next value of the second one, and vary the third one. You could do it that way as well. So based on the tree diagram, the sample space, again, is just these values across the bottom, the notation there. We could write it as they did here. The sample space is, again, sample space is all our possible outcomes, right? Okay, so we've talked a little bit about vocabulary, talked about what a sample space is, what an outcome is, an event as a subset of outcomes. I think I'm forgetting one. Oh, and a probability experiment or a trial is some process that has a random outcome. Okay, so usefulness here, we need to figure out how to figure out what the probability of something is. How do they come up with the odds for the lottery? How does C-3PO calculate the odds that Han Solo will tell him not to tell him? You know, etc. So we've got three broad categories of calculating probability. We can do it subjective probability, experimental probability, or classical probability. Uh, Subjective probability is just an educated guess. So, as they say here, that a good example is the weatherman. They examine the cloud patterns from satellite images and pressures and whatnot, and based on all of that, they're going to estimate that there's 90% chance of rain or 30% chance of rain or whatever. But it's an educated guess. Yes, it's based on a lot of information that comes in and models and how things behave. But it's still at the end of the day a guess on what things are going to do. Next, we have experimental probability, and we'll introduce some notation here during that. Probability, P, P of E is the probability that E occurs, is given by some frequency of events and number of times you've performed an experiment. So if I wanted to do experimental probability on die rolls, I'd say I rolled the die 30 times and rolled 2 ones. My probability would be 2, because I rolled 2 ones, that's my frequency, and 20 events. Sorry, 20 experiments run. So the I misused the word event there. It is very easy to slip up and switch from technical precise terms to loose imprecise common speech terms if you're not being careful. So I apologize for that. This can also be called empirical probability. And in relation to this, we do have what they call the law of large numbers that basically just says the more times you try it out, the closer you're going to be to the actual true probability. In my die roll example, assuming my die is not loaded, I should be getting, it's with a single die, I should be getting a 1 in 6 chance. And I cannot do that calculation in my head. That'd be what? 1.67, sorry, no, 16.67% probability of rolling a 1 each time. The more times I roll my dice and record that, the closer I'm going to get to that approximately 17% probability. It's going to average out in the long run. As that example shows, you can write probability as a fraction, 1 chance in 6. You can write it as a decimal, 0.1666 repeating, or as a percentage, 16.67%. They're all equivalent. Sometimes it's easier to understand things as a fraction, you have a 1 in 6 chance. Sometimes it's easier to present it as a percentage. You don't really see a decimal presentation quite as often. Although if we start, I can't remember if we get into comparing means and things like that, but you see the p-value reported in statistics frequently with experiments. They'll say this was statistically significant with a p-value of 0.012. And so that's telling you that there is a 0.012% chance, or sorry, 1.2% chance, 0.012 would be 1.2, a 1.2% chance that the things they're comparing could have been actually been the same. We'll talk about that. Maybe we'll talk about that later. But that's about the only time I've seen probabilities written as a decimal. Finally, we have classical probability. So this is the total number of outcomes that fit whatever the event is over the total number of outcomes in the sample space. This is kind of like, you could kind of look at it as, let's go back here, experimental probability is, you can think about this as the sample statistics. You've done a sample number of experiments, and these are your results. And this would be, conceptually similar to your population statistics. This is the actual number of possible outcomes that, the actual number of outcomes that are in this event, and this is the total actual number of outcomes possible in the sample space. This is also called theoretical probability, and it is the most precise type. So again, we've got an educated guess, what the weatherman might tell you. Hopefully it's a well-educated guess, and you can use it. You have the experimental probability, which is based on some number of experiments. And then you have classical probability, which is when you actually do know all the possible outcomes and everything about the sample space. All right, so let's look at some probability examples. What kind is this? Is this going to be classical? Is this subjective, experimental, or classical? The odds of picking the Queen of Spades out of a well-shuffled deck of cards. Just note your answer, and we'll move on to the next one. We have an economist predicting a 20% chance that tech stocks will decrease over the next year. Okay, I've got my answers for those two. Let's move on. We've got a policeman wanting to know what the chances are that a randomly chosen driver will be driving drunk on a Friday night. So he does an experiment and records the number of drivers stopped at a roadblock and the number of drivers over the legal limit, and determines the probability is 3%. What type of probability is that? Remember, we've got subjective, empirical, or experimental, and classical or theoretical. All right. So, in part A, pulling out a single card, we know that there are 52 cards. We know, assuming it's a standard deck, that we know what each of those cards are. It well shuffled means it should be equally likely to occur, so this is a classical probability. We know all the outcomes. We know everything's equally likely, and we can know everything in that event space. Similarly, if we want the probability of pulling a queen, that would be 4 in 52. Again, we know all of the outcomes. We know all of the results that fit in that event. Okay, so next one, the economist is giving an educated guess, based on current trends and what he thinks is going to be happening in the future. Tech stocks are going to likely drop. The last one, he is performing an experiment. He is not evaluating all drivers, because not all drivers would be stopped at that roadblock, not even all drivers in that area or at that time of day in that area. Some people may have cut their trip short before the roadblock or taken an alternate route, whatever. So he can't evaluate all drivers. So the probability is experimental. Okay. All right. So we have a guy who's allergic to peanuts, and he goes to a party, and the notices that there are 34. What's this? 42 slices of cheesecake. 12 of which have peanut butter. Now, assuming these are distributed at random, what is the probability that his cheesecake contains peanuts? All right, so this is classical probability, as it says. Take a moment and think about how many possible outcomes there are and how many outcomes fit into our event of Beck's cheesecake containing peanuts. Move on when you're ready. All right. A similar calculation, what are the probabilities that his dessert does not contain chocolate? We've got 10 slices of chocolate and 12 slices of peanut butter chocolate. I'm going to assume the caramel and the strawberry do not contain chocolate because that would make the problem very difficult. Okay. So we've got 12 slices with chocolate peanut butter and 42 pieces total. Probability is the total number of things that fit our event over the total number of possible outcomes. So we've got 12 in the event, 42 possible. We can simplify that to 2 and 7, or go with the decimal, or call it 28.57%. All right, here we've got 12 plus 8, so it'd be 12 caramel, 8 strawberry that do not contain chocolate. Same calculation, same formula, the number that fits our event and the total number of outcomes in the sample set. We get 20 over 42, or 47.62%. Okay. Alright, so if we've got a beginning archer who only hits the target 50% of the time, or as in my case, if I were to take a bow out now, as I'm very rusty, 50% of the time might be generous. What are the probability in 3 shots that the archer will hit the target 3 times? So it's 50% for each shot. What is the cumulative probability? This might be a good example where a tree diagram would work. We've got a hit and a miss. If you hit, you've got a hit and a miss. If you miss, you've got a hit and a miss. That might be a good way to diagram this. All right, you can either use a pattern or a tree diagram. They chose a tree diagram. It's fairly useful. The way to visualize this: hit, miss, hit, miss, hit, miss. So each shot is independent of what happened before. Shot 1 could be a hit or a miss. Shot 2 could be a hit or a miss, but we can organize our data this way. So there's only one possibility that gives 3 hits out of 8 total possible. So our probability would be 1 in 8, or 12.5%. All right. So we've got a family with 6 boys. What are the chances the 7th child is going to be a boy also? You know, there are always people who want one child or the other. I did used to know a guy who had 6 girls before they stopped trying because he really wanted a boy. So you might think, you know, maybe it's due. You're due for something. So one way to look at this would be to take the overall entire probability set, every combination for birth orders of 7 children. We saw the combinations with birth orders of 3 children already in tree diagrams, so that'd just get significantly larger as we got down to 7 children. We do know that the family already has 6 boys, so we could start with a subset. We've got just these two as possible outcomes: 6 boys and 1 girl, or 7 boys. Those are our 2 possible outcomes. The possibility of baby number 7 being a boy then is 50%, just as with any other pregnancy. Another good example is genetics and disease genetics. So what are the chances that somebody has inherited a mutated Huntington gene from either parent and will develop Huntington's disease? So if somebody with the disease has a child with the person who's got the genes but they're not mutated, so they don't have the disease, what are the probabilities that their child will develop Huntington's? So they're going to talk a little bit about a different type of diagram. You've probably seen similar things with talking about eye colors and such, when you're talking about genetics, I've seen these in basic biology. So they're going to make this square matrix. They're going to use an uppercase H for the mutated Huntington's gene that will cause um, cause the problems, and that lowercase h for non-mutated ones. Um, they're going to need to make some assumptions because we don't necessarily have enough information to not. So we'll assume that the mother only has one mutated gene, and the father has two unmutated genes. So we've got the father on one side with two unmutated genes, the mother on the other side with the two mutated genes. You only need one mutated gene to develop the disease. So, we just match these up to fill in the square. Mutated, unmutated, 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 mutated, unmutated, etc. So we've got two outcomes that fit in our event of the child coming down with Huntington's, and 4 total outcomes. So our probability of that event is 2 in 4, or 50%. Okay.